Okay, this is section 2.3, part 2. We're going to start with example 5, and we're going to talk about finding the zeros of a polynomial. So finding the zeros means f of x equals 0. This is higher than a quadratic, so I cannot use the quadratic formula yet, but I can factor. I have a common factor of x. Now I could use the quadratic formula to find this part, but I can also factor it. And things that multiply to -6 and add to -1 are -3 and +2. Now to get my solutions, remember that 0 times anything is 0. So any of these terms can equal 0. And the whole thing will equal 0 when any of them equal 0. So I'll have 3 solutions here. One of these is 0. This one, I move the 3. I add 3 to both sides. I get -3. I subtract 2 from both sides. I get -2. So I know my 3 zeros are -2, 0, and 3. Those could also be thought of as my 3 roots or x-intercepts. I can now sketch this graph without even needing my calculator, because I can plot these 3 points. I know it's a cubic, it's a positive one, which means it goes from down up. End behavior is down, so it's got to start down over here on the left, come through these points, and pop back through and end with end behavior that is up. I can verify this by looking at my graphing calculator here. I can also go ahead and find the zeros. I'm just going to find one of them by using, with my calculator, second trace 0. And I believe you've all used this. Left bound, right bound. Those are my solutions, -2, one of them. Okay. So factoring, finding zeros, quadratic formula as well sometimes, will help us find the zeros by hand. You will have to be able to do that. But once I know the zeros, I can start drawing the graph. But I introduce an interesting question. What if a 0 occurs twice? Say I have a function like g of x equals x plus 2 squared and x minus 1 cubed. This is essentially x plus 2, x plus 2, x minus 1, x minus 1, x minus 1. This is a 5th degree or a quintic. This one has zeros at -2, because -2 plus 2 is 0, and 1 minus 1 is 0. We call these multiplicities. So I could say my solutions are -2 multiplicity 2, because it shows up twice. And 1, and I usually abbreviate multiplicity multiplicity 3, because it shows up 3 times. This is a quintic. The leading coefficient here, there's no negative in front of any of my x's. The leading coefficient's positive, which means it's down on the left and up on the right. A multiplicity 2 root will touch the axis and bounce off. A multiplicity 3 root goes through at this kind of funny thing where it switches from hooking away from the axis to hooking through with what's called an inflection point. Okay, it kind of switches the way it's curved. Looks like the middle of a cubic. So if I have a multiplicity 3 root, I have an inflection point on going through the x-axis. You can have inflection points elsewhere as well, but if I have a multiplicity 3 root, it's got the inflection point going through the axis. This one, multiplicity 2. And that's bouncing off the axis, just like x squared. Okay. Oh, I didn't draw that one right. Oh, I did a different function than they did in the book. The book switched it up slightly from what I did. They had x plus 2 cubed and x minus 1 squared. Again, I can draw this without needing a graphing calculator. I know my two roots are -2 and 1. I know I start down on the left. Because this is multiplicity 3, I have to make that inflection point going through at -2. And somehow I've got to get back down to the axis here and bounce off at 1. So changing those multiplicities changes the function and the graph a little bit. We have a little theorem we call the intermediate value theorem. Okay? The intermediate value theorem says if a and b are real numbers where a is less than b and f is continuous on the interval ab, doesn't have to be continuous everywhere, just between a and b. So let's take a look at a graph and think about this. Here's a graph. A, B. My interval from A to B goes between the dashed lines. Says then f takes on so here, f of A is the y coordinate here. F of B is the y coordinate at B. So this is the point A, f of A. Those are the coordinates. Up here, the point is B, f of B. It doesn't matter how this bounces around, whatever it does in here. If it goes through those 2 points, every value, every y value between f of A here and f of B here will have some value that covers it. There might be some that go outside, like here. All the theorem says is everyone will be there, but the condition that it's continuous from A to B must be met for this to matter. Okay, we're going to talk a little bit about designing a box. We're going to do example 9, and then I'll come back to example 8. So example 9, the Dixie Packing Company has contracted to make boxes with volume approximately 484 inches cubed. Squares are cut out of the corners of a 20 by 25 inch piece of cardboard. The flaps are folded up. We did something like this the other day. We called it the box problem. This is 20, 25. We're taking x out of the corners. Giving us here 20 minus 2x for dimension. And 25 minus 2x. Thus, my volume equation is length times width, 20 minus 2x, times height, x. So 25 minus 2x times 20 minus 2x times x. Okay. I want to know when it equals 484. I'm going to go to my graphing calculator to solve this. And I'm going to start with my first volume equation. They used x. And I'm going to do 484 here. Okay. My window. Well, I know x can't be less than 0. And I know it can't be larger than 10 because 10 would be 20 minus 2x. I can't have a negative length. So 10 would give me a 0 length, which I also really can't have. My y min, I'll leave it at -10. I need to be larger than 484. I'm just going to go 1,000 because I kind of want to see the top of this because I think I need to answer that later. And now I'm going to graph that. So I see that there's two different sizes I could cut the square to get 484. So I will go to my second calc menu and intersect first curve, second curve. My guess, since I've got two of these, it will go to whichever one I'm closer to. So I know x can either be 1.222, or to find the other intersection, I do the same thing. See which curve I'm on. I scrolled away to see which curve I was on. My guess is closer to the second intersection, or 6.87. So again, I'm looking at x equals 1.22 or x equals 6.87. This particular problem does not ask me for it, but oftentimes they'll ask you for the maximum. To get the max, second calc max, and get to my left side of the maximum, the high point. .68. Okay. Does that make sense? The last thing we're going to do is search for hidden behavior in a graph. And again, this is using the graphing calculator. So I'm going to clear out what I have. I'm going to enter what's in example 8. This is a very carefully crafted function to have some hidden behavior. That's hard to see when you first look at the graph. Okay. Keep an eye out for hidden behavior on tests. Hint, hint, hint. And I'm just going to start with Zoom standard. That's what I usually start with unless I have some sort of hint. I cannot see the bottom here. If I need to see the bottom, I'm going to zoom out my Y's. I'd go 50 or 100. Here you can't really tell the hidden behavior at all. Now I can see this bottom. This looks kind of like an inflection point. But I can't tell and know for sure that it only crosses the axis once and that it's an inflection point until I really zoom in on that. How am I going to do that? Well, it's around 1, so I'm going to go from 0 to 2. I think that'll capture it on the axis. And I'm going to go from way in on the y's, -1. Oh, I forgot I can't use the minus button for negative. To 1, not 11. 11's too big. Scale can be 1, I don't really care. This is supposed to cross. I must have a little typo. I can see, though, that I've got humps here. Why did I mess up? It's not 0.14x, it's 0.1x cubed. Now I can see I have 3 actual zeros here, a max and a min. It's not an inflection point. Make sure that you zoom in at inflection points if they're going across the axis so you don't miss hidden behavior. Okay? That is it for section 2.3.